All right, ladies and gentlemen, welcome back to 6.5, finishing up our study of polar graphs. All right, so we're going to look at some very interesting curves. I think they're pretty cool looking. Desmos does work for this stuff, so I'm going to show you a little bit of Desmos on this. All right, so the first thing that we want to discuss is how to test symmetry. All of these graphs that we're going to be looking at have some form of symmetry on them, and there's really only three types. We have symmetry about the x-axis, which means it's line reflection. There's a line reflection, so it's same on the top as it is the bottom. There is symmetry about the y-axis, and there is symmetry about the origin, which means it's a rotation. And in order to test symmetry, we do a very simple test, one or the other here. Wherever we see an r and a theta, we're going to replace it with r and negative theta, or negative r and pi minus theta. And this goes along the lines of finding the coordinates. Remember, we had coordinates that are on one side of the, we had a coordinate here that could be listed as r theta, but it also could be listed as negative r and theta plus pi. And that's actually kind of where this comes from. All right, so if we want to test about the x-axis, we do r and negative theta, or this other version. If we want to test to see if it's symmetric about the y-axis, then we test everywhere we see an r and a theta, we plug in negative r and negative theta. And essentially what we're trying to do is we're trying to say if we plug those things in and we get out the original equation, then it's symmetric about either of these. And same thing to go with about the origin. If the opposite of r and the same theta come out to the same original equation, we have symmetry about the origin. And this is exactly what we used to do with even and odd functions. If I said f of x is equal to 3x minus 1, and you wanted to know if it's even or odd, or neither really, you would plug in a negative x. And you'd get 3 times negative x minus 1, you'd get negative 3x minus 1. And negative 3x minus 1 is not the same equation, and therefore it's not an even or odd function. This one has no symmetry, actually. So let's see what it's going to look like for an example here. So we want to know what's the symmetry of this particular equation. Now you might look at this and go, hey, this looks pretty similar to what we did in the last lesson, and you're correct. However, in the last lesson, we were strictly looking at r equals for sine theta, and that just gave us circles. This gives us a much more interesting graph. Much more interesting. We'll describe them a little bit later. So if you were to graph this in polar mode, just if you have a calculator handy, go ahead and do it. I'll show you. I guess I'll show you what Desmos looks like right now. So Desmos is here somewhere, I thought. Where did I put it? Oops. Here's Desmos. Get rid of that 1. And we're saying 3 theta. Let's graph that. You get something that looks like this. Now, this particular equation looks like it's symmetric about the y-axis. Some of you might be thinking that it looks symmetric about the origin where we can rotate it, but rotation must be less than 360. And the only way we get back to the original formula or the original graph here is if we rotated 360 degrees. All right, so let's go back to, see if I can figure out how to do this here. Let's go back to this. And if you were to graph that in polar mode, like you just noticed, you would get that little like pinwheel effect there. And you'll notice that it actually graphs in such a manner on your calculator. Obviously, Desmos does it instantly for you. We notice that it's symmetric about the y-axis. Oh, and by the way, do this in radian mode. Go from 0 to 2 pi on your t or theta min, theta max, that sort of idea. Okay, so theta goes from 0 to 2 pi. So because we think it's symmetric about the x-axis, we verify this algebraically by substituting in negative r and negative theta to see if we get the original function. So I take r equals 4 sine of 3 theta. I plug in negative r and negative theta, and I see what I get. Well, I know, and you might remember, that sine of a negative angle is the same as the opposite of the sine of that angle. So all I did was change the negative here with the 3, which is legal. I just know that the sine of a negative angle is equal to the negative sine of that positive angle. That's our odd identity on our identity page. And then you notice I have a negative equals a negative, means I can divide both sides. And since this equation is now identical to the original equation, that verifies algebraically that this is symmetric about the y-axis. Okay? And if you're looking at a problem and you go, hey, it looks like it's symmetric about the y, but this didn't work, that's when you use the other statement, the or statement. So you try again. Because sometimes it only works for certain ones. All right, let's get into the more interesting things. This is kind of a short video, just kind of looking at the graphs themselves. The rose curves, these ones are probably the best looking ones. These are in the form, one or the other here, if you have r equals a cosine in theta and r equals a sine of in theta, where n is just any integer, as is, and a is just any number. So integer being a whole number that's on a number line, and a being any number you want. The domain of these functions is all real numbers. The range ranges from the negative a value, or the negative absolute value of a, to the positive absolute value of a. So the distance being range represents the distance from the origin. So the distance from the origin has to do with this a. Now here's what's cool. You can look at these equations and determine symmetry, even though you'll still have to verify it. Both of these graphs are symmetric about the x-axis, the y-axis, and the origin. They have all three types of symmetry if n is an even number. It doesn't matter what a is. If n is an even number, it has all types of symmetry. That's kind of cool. If n is odd, for cosine, it's symmetric about the x. And if n is odd, for sine, it's symmetric about the y-axis. The maximum r value, or the maximum distance from the origin that your graph will get, is a. And here's the cool thing. The number of petals on your graph. Okay, so we graph that pinwheel looking thing. We would say that has 3 petals. And if you know that we graphed, what would we graph? Sine, I think? One or the other. Yeah, sine of 3 theta. There were 3 petals because the n was 3. So if you let n be an odd number, you get n number of petals. If you let n be an even number, you get twice that many petals. And what we're going to do is we're just going to graph a few of these. If you have your own graphing calculator, do this. This is kind of fun. If you want to kind of do a little bit of Desmos stuff, I'm going to show you how to do this. And I need to delete those things. Here is what I want to think about. Dang it. When you are on Desmos, here's something you can do. You can let this be B, And if you type in b, you go r equals b sine of whatever. You let b be a slider, and you can change b from, let's only do positive numbers, 0 to, let's go to 10, I don't know. Steps don't really matter for this one, for us. We can go by decimals, which is what they're going to do. And let this be a. And if you didn't have, I already had this a down here, but if you typed a there, it would also ask you to add a slider, which this slider is super fun, cool, I guess, I don't know, because you can change your equation as you go. So I want a b of 4, so I'm going to go out 4 units from the origin. Notice this petal up here. Now notice that I have an odd 5, and look, I have 5 petals. And because it's sine, you notice that it's symmetric about the y-axis. But let's look if I made it 6. If I made it 6, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 petals. There's still 4 units from the origin, that length. And that's really it. I mean, these are so cool. You can just do 7, and then 8 makes 16. 9 makes 9. 10. But what you'll notice with the even number, let's go even, nice, easy even number. Notice that this particular graph is symmetric about the y-axis, symmetric about the x-axis, and has rotational symmetry about the origin, which means it has all 3 because that in value is even. I guess I should have used a and n here, but I hope you get the idea. Let's see what happens if we make it cosine. We can just do cosine. Same idea. The slider for b here, the length of the petal is still the same. Changing this, now you notice that cosine starts over here on the x-axis, where sine started on the y-axis. But we just keep moving, and we get the same kind of idea, only in cosine's case, we always have a petal on the axes, especially when it's even. Okay, so these are kind of cool functions, I think, or cool equations. They're not technically functions, they're polar equations. But you can tell a lot of stuff just before you even do any graphs. You can tell a lot of things just from this statement right here. All right, the next type of function or equations that we're dealing with are this new word for us. This is Limasonn. And if you looked in your textbooks, you would see, I think this textbook does it. Some textbooks do, some textbooks don't. This has like a little curly Q thing. I think it's either that way or the other way. It doesn't matter to me, really. I think it might be that. I just don't have that symbol on my computer. So this is a Limasonn curve, and Limasonn curves look like this. So it kind of looks the same as before, only in this case we have something plus b cosine theta or something plus b sine theta. And a and b are both bigger than 0, right? Because b is bigger than 0, but we can do minus. That's not a big deal. Again, kind of the same idea here. Domain is all real numbers. The range goes from a minus b to a plus b. Symmetry. The sine version has symmetry about the y-axis, and the cosine version has the symmetry about the x-axis. And that should make sense. Sine is the y-coordinate, cosine is the x-coordinate, so that should be kind of easy to remember. The maximum distance from the origin that your graph will get is a plus b units. Big if here. If a over b is less than 1, then we have an inner loop. There are 3 different types here. If a over b is equal to 1, then it's called a cardioid. And if you kind of look at this word, it might look a little familiar because the first 6 letters is cardio. and cardio represents heart. So this one should look a little bit like a heart. And if A over B is between 1 and 2, it's called a dimpled Limasonn. Oh, sorry, I had 4 of them here. And if A over B is greater than 2, then it's convex. I'm going to let you give a second here. And I'm going to go to Desmos, kind of do this kind of same sort of thing. And just kind of have fun with it. Just kind of change numbers around here. There we go. Forgot where I was going. And let's kind of do the same thing. Let's just start over here. I've got to get rid of my pen. Let's just start over. And I'm just going to go like this. I'm going to go A plus B. So I actually want more things here. So let's go cosine. Whoa, what's that? Cosine of. Well, I guess we didn't have more than that. So if you come down here to your keyboard and go ABC, here's your theta button. And I'm going to add sliders for A and B. And I'm going to let A be, I don't know if I let, actually let's do the sine version. I like the sine version better. If I let A be 1 and B be 1, notice I get that cardioid. It kind of looks like an upside down heart. So let's make this -1. Ha. All right, so if I make B -1, I'm going to change this. I'm going to change going from -10 to 10. Oh, A is never negative, so A is 0. And a step of 1. I'm going to change B from -10 to 10 with a step of just 1. I don't really want any decimals in this case. All right, so let's zoom in. So you notice here, it has symmetry about the y-axis. It kind of looks like a heart. I know it's not exact, but hearts don't really look like the picture that you guys always draw. And notice that A over B is 1, and that represents my cardioid. What if it was less than 1? So notice I get that inner loop. I get that inner loop here. Kind of looks like a cardioid, but it has an inner loop. If you graph it on your calculator, it looks a lot cooler when it has to graph because it does this little loop-de-loop-de-loop. Okay. Let's see. What's the other one? Greater than 2. So let's move this one all the way up to 6. No, let's not go to 6. Let's go to 4. And we'll go back this one to a 1, 2. So this one's equal to 2. So notice this little dimple thing here. It's kind of weird. Not 1. Let's go that way. There's a little more dimpled there. Between 1 and 2. And if we go all the way back to 1, then we have a convex, and it kind of just looks like a circle. And that's kind of what happens there. But notice how cool this is with Desmos. You can't do this with your calculator this quickly. You can see the effect of B just by sliding this B value back and forth. So notice if B is positive, it opens up that way. If you get an A minus B, it opens up this way. And likewise for cosine. So this is kind of cool. I mean, I have no idea what's going to happen if I type in tangent here, but that's kind of weird. I've never seen that before. But this is really kind of cool with the sliders on Desmos. So hopefully you get a little bit familiarize yourself with that. All right, let's go back to the PowerPoint here. What do we got left? Hey, there we go. You are going to be asked to analyze some of these functions, 1 or 2, I think. And when you analyze the function, you want to make sure you basically do what I did on those 2 pages. You want to describe the domain, the range, what type of symmetry it has, the maximum R value, what's the max distance that the function will get from 0, or from the origin. And if it's a rose curve, tell me how many petals it's going to be. All right, that is it. Kind of a nice, short and sweet lesson. I hope everybody, again, becomes enlightened on these new functions, these new cool little functions. All right, see you guys tomorrow.